Hello, my name is Randall Crutcher, and this is my mapping demonstration. So what we're going to look at is some genotypes. If I can get my computer to work here. So of the provided genotypes, we were given 8. The two parentals are the ones with the largest number of progeny. So that's why the plus 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 and the ABC were selected. The two genotypes with the lowest number of progeny were selected as the double crossover recombinant variants. That's why the A++ and the plus BC were selected. And the remaining are single crossover recombinants. So that's how the order was kind of selected there. That's why the parentals were the ones that I chose there. So now we need to find the middle gene, and to do this we compare the parentals with the double crossovers, and so that's what we've done here. And the only different gene is the middle one. In this case is A, and so then we just arrange the genotypes in sequence to determine the middle genes. And so that's, what I've done here is with the new gene sequence, we're just kind of rearranged. So you'll see the BAC instead of the ABC, and you'll see the plus A plus and the B plus C and the double crossovers, in place of those. And then, for the singles, we also rearrange those guys there. So, so now that we have the order established, we need to try to map these out. So we're going to look at here. Here's kind of like a crude map of what I've calculated, and I'll kind of go through this. But these are centimorgan units right here. So the B to A distance, how we figure that is we take the double crossovers and the single crossovers, add those together, and divide by the total number of offspring, and multiply it times 100. And so if you follow right here, you'll see that right there. We've taken the double crossovers and the single crossovers, and I've done the simple math there to figure that out. It's 18.46 centimorgans, and so that's a little distance there between those. We've done the same thing over here with the A to C distance. We've taken the double crossovers and plus the single crossovers, divided by the total number of offspring, times 100. So I've done the math here. Check me on that if you would like to, but I'm pretty confident it's right. I've looked at it a couple times. So that's pretty simple stuff right there. Gets a little bit more head scratching as we move along. You'll see some of these other calculations that we're going to look at. Here is my crude little map from B to A to C with the 18.46 centimorgans and 38.66, which leaves us about, just a little tad over 52. I think it's 52.16 from B to C. And so to calculate the coefficient of coincidence, or the COC, we take the actual double crossover over the expected double crossover. So the actual is, we just get those from the from here, and then plug those in here over the total number of progeny, and it gives us 0.0418. And the expected is a little bit, I had to kind of dig around to find this. Expected double crossover, I take the 18.46 here, and the 38.66, divide both those by 100 and multiply that times 57 or 5,742, which gives us 409.78. Okay, so what does all that go into? So the coefficient of coincidence is 240 divided by 409.78, which gives us the number that kind of will help us along here, is 0.585. So what we do with that, we take the 0.585 from 1, and that gives us 0.415. So that's the interference. And the interference, if the interference is less than 1, it's a positive interference, which implies that the chances of a double crossover is less if one crossover has occurred. Now, if it were more than 1, that'd be a negative influence, and that would imply that the chances of a double crossover is more if 1 had occurred. And then there's a case where it could be 0 if you got 0. If you got 1 here, and 1 minus 1 would be 0. In that case, there'd be complete interference, and no double crossovers would occur. All right, thank you.